Welcome to Lab 2 of the Signal Integrity Basics series. This lab dives into the topic of transmission lines in PCB design. This session will provide a foundational understanding of how PCB trace properties directly influence signal integrity. The objectives for this lab are to effectively edit transmission line properties within a professional simulation environment, to comprehend the electrical implications of varying these properties, specifically focusing on the characteristic impedance, propagation delay, and signal loss, and to gain familiarity with different transmission line topologies and their respective behaviors. In modern PCB design, particularly with fast switching signals, a simple copper trace can no longer be considered merely a conductor. Instead, it functions more like a transmission line, a precisely engineered structure designed to efficiently guide electrical energy. The integrity of high-speed signals hinges on the thorough understanding of these structures. Key characteristics such as characteristic impedance, propagation delay, and signal attenuation become paramount. These factors dictate whether a signal arrives at its destination cleanly and without distortion. Failure to account for transmission line effects can lead to significant signal integrity issues, compromising system performance. To begin our practical exploration, we'll utilize Siemens HyperLynx SI. Please navigate to your SI Basics lab directory via Windows File Explorer. Double-click on the Launch HyperLynx SI icon and confirm the license dialog, and then click Done. Next, we'll open the schematic file for this exercise. Select Browse, Line Sim, Projects, and then Open Schematic. Locate your directory within the HyperLynx Workshops folder, then navigate to the Transmission Lines lab. From here, you will open the file tlineproperties.ffs. Click OK on the subsequent dialog boxes. Begin by examining a transmission line from the single-ended 50 ohm group. Double-click on TL9 to open the Edit Transmission Line window. Observe the Transmission Line Type tab, which indicates uncoupled single line type with the Stackup selected. It is important to clarify the term Stackup here in this context. A PCB stackup refers to the precise arrangement of metal layers and dielectric materials that constitute a printed circuit board. This layered structure defines critical electrical elements such as impedance and capacitance, and a stackup transmission line signifies a trace that's modeled directly within this defined PCB layer structure. To the right of this window, you'll see the electrical properties are displayed: Z0, R, and delay. Z0 represents the characteristic impedance, R represents the resistance, and delay quantifies the time required for a signal to traverse the length of the line. The hints section provide contextual guidance for the line type selected. Now, select the Stackup tab. Here, we can observe that this specific transmission line is situated on layer 1 signal top, with an initial length of 3 inches and a width of 7 mils. The electrical properties section provides further detailed information regarding this configuration. We'll start by experimenting with the length of the transmission line and exploring what happens to the electrical properties. Start by changing the length from 3 inches to 7 inches. Observe the electrical properties section carefully during this adjustment. Upon increasing the length, the delay value increased, which is an intuitive outcome. A longer physical path necessitates a greater propagation time. However, it is critical to note that the Z0 characteristic impedance remained unchanged. This observation highlights the fundamental principle that the characteristic impedance of a transmission line is independent of its physical length. Impedance is determined by the line's cross-sectional geometry and the surrounding dielectric environment, not its overall length. Next, we're going to take the stackup line and modify its width. Return the length to 3 inches and reduce the width from 7 mils to 5 mils. Again, monitor the electrical properties for changes. In this instance, the Z0 value has changed. It increased. This behavior can be understood by considering the trace and its reference plane as a parallel plate capacitor. A reduction in trace width effectively decreases the area for this conceptual capacitor. As capacitance decreases, the characteristic impedance increases. This relationship is pivotal for achieving precise impedance control in PCB layouts. Therefore, narrower traces generally result in higher characteristic impedance, while wider traces lead to lower impedance, assuming all the other parameters are held constant. Next, we will experiment with transmission line topology. Return to the Transmission Line Type tab and select Microstrip. You will observe that the Values tab automatically activates, prompting for additional parameter inputs. A microstrip is a widely adopted transmission line configuration where the signal trace is routed on an outer layer of the PCB, with a continuous reference plane positioned directly beneath it. This differs from a Stackup type we previously examined, which could represent on an internal layer. Microstrip models require more parameters due to their exposed nature and dependence on additional dimensions, such as the trace height above the ground plane. Let's evaluate the impact of length modification, this time for the microstrip. We will adjust the length to 5 inches. Consistent with our prior observation, the delay increased, while Z0 remained unaltered. This reinforces the principle that length primarily influences propagation delay and signal loss, but not the characteristic impedance. We will now reset the length to 3 inches. Modify the width of our microstrip now to 3 mils. Based on our previous findings, what change would you anticipate for Z0? Well, as anticipated, the Z0 value increased. Making the signal trace narrower elevates the characteristic impedance. This outcome aligns perfectly with our parallel plate capacitor analogy. Reduced capacitance inherently leads to higher impedance. We'll now revert the width to 5 mils for our final experiment. Here, we'll adjust the dielectric constant to 5.3. This change alters the material properties of the insulating layer between the trace and its reference plane. Observe that the Z0 decreased substantially, and concurrently, the delay increased. Let us analyze these effects. A higher dielectric constant signifies a material's greater ability to store electrical energy. In our capacitive model, this translates to an increase in effective capacitance. As previously established, an increase in capacitance leads to a decrease in characteristic impedance. The increased propagation delay is also an expected consequence. A larger dielectric constant directly causes a reduction in the signal's propagation velocity. Therefore, a higher dielectric constant results in a slower signal velocity and, consequently, a greater delay over a given length. This experiment demonstrates why the selection of PCB dielectric materials is a critical consideration in high-speed design. Some key takeaways from this lab. Transmission line length primarily affects propagation delay and signal loss, but not characteristic impedance. Trace width directly impacts characteristic impedance. The dielectric constant significantly influences both characteristic impedance and propagation delay. I encourage you to continue exploring various transmission line types and parameters. Hands-on experimentation will significantly enhance your intuitive understanding of signal integrity principles.